something changed inside the Earth, and the scientists who spend their careers listening to the planet went quiet in a way that people who study planetary interiors almost never go quiet. Not because the signal was subtle, it was not subtle. Not because the instruments that detected it were operating at the edge of their sensitivity, straining to pull a whisper out of noise. The signal was clear. It was coherent. It was reproducible across multiple independent monitoring stations on multiple continents, verified by teams that had no prior communication with each other before their data converged on the same anomaly. The scientists went quiet because the signal was saying something that the models they had spent decades building had not predicted. Something that the best available understanding of how the Earth's deep interior works had not suggested was possible with this timing, this character, this geometry. Something that required them to sit with the data for longer than they normally sit with data before deciding what to say about it publicly. Because what the data appeared to be saying was going to require either a new explanation or a revision of explanations that had seemed settled. The Earth's core is the least accessible place on the planet. It is also, in a specific and measurable sense, the most important. Everything that makes this planet habitable, the magnetic field that deflects the solar wind and prevents the atmosphere from being stripped away the way Mars's atmosphere was stripped away, the heat that drives the plate tectonics that recycles the carbon and nitrogen that living systems require, the dynamic interior that has kept this planet geologically alive for 4.5 billion years while its neighbours went quiet. All of it originates in, or is sustained by, what is happening at the centre of the Earth, 5,000 kilometres below the surface, in a place that no instrument has ever directly sampled, and that no human being will ever visit. What scientists know about the Earth's core, they know entirely through inference. Through the behaviour of seismic waves that travel through the deep interior and emerge at the surface, carrying information about what they passed through, encoded in their arrival times, their amplitudes, and their waveform shapes. Through the measurement of the magnetic field at the surface, which reflects the behaviour of the liquid ion that generates it in the outer core, through the process called the geodynamo. Through laboratory experiments that recreate the extreme pressures and temperatures of the deep Earth in diamond anvil cells, and shockwave experiments, and try to characterise the properties of iron and iron alloys under those conditions. Through the numerical simulations that combine all of this information into computational models that attempt to reproduce the behaviour of a system that operates at scales and under conditions that are fundamentally beyond direct human observation. The signal that just arrived from the Earth's core came through the seismic network. It was detected in the data from the global network of seismometers that has been operating continuously for decades, recording the passage of seismic waves from earthquakes around the world and transmitting that data in real time to processing centres where algorithms and human analysts work together to extract the information the waves carry. Most of what the seismic network detects is routine. Earthquakes occur constantly, thousands of them every day, at magnitudes too small to be felt, but large enough to be detected by sensitive instruments. The seismic waves from these earthquakes travel through the Earth, along paths that depend on the properties of the material they pass through, bending and reflecting, and converting between wave types as they encounter boundaries between layers of different density and composition. The global seismic network has been accumulating this data for long enough that the expected behaviour of seismic waves travelling through the Earth is very well characterised. Anomalies stand out against that well-characterised background with a clarity that makes them immediately recognisable to experienced seismologists. The anomaly that triggered the quiet was not in the timing of seismic wave arrivals in the way that most core-related seismic anomalies manifest. It was in the polarisation of the waves, in the specific orientation of the ground motion they produced as they emerged at the surface after travelling through the deep interior. The polarisation of seismic waves is sensitive to the alignment of structures and anisotropies in the material the waves travel through. When waves pass through a material that has a preferred alignment, a fabric or texture in the deep rock or metal caused by the history of deformation and flow that the material has experienced, the waves emerge with a polarisation that reflects that alignment. The polarization signal that the network detected was inconsistent with the alignment that decades of accumulated seismic observations had established for the inner core. The inner core, the solid iron ball at the center of the Earth with a radius of approximately 1,200 kilometers, was showing a different seismic fabric than it had shown in the data accumulated over the previous decades of monitoring. The inner core rotates. This is one of the most remarkable facts about the Earth's deep interior, and it was one of the more surprising discoveries of deep Earth seismology when it was first proposed in the 1990s and subsequently confirmed by multiple independent lines of evidence. The inner core rotates independently of the mantle and the crust above it because it is decoupled from the overlying material by the liquid outer core, the layer of molten iron that surrounds it, and that is itself rotating and generating the magnetic field. The rate of the inner core's rotation relative to the mantle above it had been measured by comparing the travel times of seismic waves that pass through the inner core at different points in time, using the assumption that any change in travel time over time reflects a change in the orientation of the inner core's seismic anisotropy relative to the wave path, which would occur if the inner core is rotating at a different rate than the surface from which the waves are launched and at which they are recorded. The measurements of inner core rotation rate that accumulated over the decades of the global seismic network's operation had produced a picture that was scientifically fascinating and that had required significant revision over time as more data became available and as the analysis methods improved. Early studies suggested that the inner core was rotating faster than the mantle, completing an extra rotation relative to the surface approximately once every 400 years. Later studies using larger datasets and improved analysis methods produced a range of estimates that were in poor agreement with each other, with some studies suggesting super-rotation, faster than the mantle, some suggesting sub-rotation, slower than the mantle, and some suggesting that the rotation rate had changed over the period of observation, that the inner core was not rotating at a constant rate relative to the surface, but was instead oscillating, speeding up and slowing down in a pattern that had a periodicity of roughly 7 decades. The study published in early 2023 that proposed the inner core had recently stopped its rotation relative to the mantle and was beginning to reverse direction generated significant public attention and significant scientific debate simultaneously. The proposal was based on the analysis of seismic wave travel time data spanning several decades and on the interpretation that the reversal in the trend of travel time changes represented a reversal in the direction of inner core rotation. The authors were careful about the interpretation and about the uncertainty associated with it, acknowledging that the seismic data alone could not definitively distinguish between a rotation reversal and other explanations for the observed travel time changes. The scientific community received the paper with interest and with the healthy skepticism that accompanies any major proposed revision to the established understanding of a fundamental Earth system. Subsequent studies re-examining the same data and additional datasets produced a range of interpretations that did not converge on a consensus, which is itself scientifically informative. The inner core is doing something. Exactly what it is doing and what it means for the systems that depend on the deep Earth's behavior remains a question that the data has not yet fully answered. The signal that the monitoring network just detected added a new dimension to this unresolved debate. The polarization anomaly was not something that could be explained by a simple change in rotation rate or rotation direction. It required, in the preliminary analysis conducted by the teams that first identified it, a change in the seismic fabric of the inner core itself, in the alignment of the iron crystals that constitute the solid inner core and that give it its seismic anisotropy. The fabric of the inner core is believed to reflect the history of its growth and deformation. As the inner core grows by the solidification of iron from the surrounding liquid outer core, the crystals of iron that form at the inner core boundary develop a preferred orientation that reflects the pattern of heat flow and solidification at the boundary. Over billions of years of growth, this crystallization fabric has accumulated to produce the anisotropy that seismic waves detect as they travel through the inner core along different directions. The fastest direction for seismic wave travel in the inner core is approximately aligned with the Earth's rotation axis, a feature that is consistent with theoretical models of inner core solidification and growth, but whose exact origin is still debated in the geodynamics literature. A change in the polarization signal emerging from the inner core in the current monitoring data implies that the fabric the waves are traveling through has changed. That the alignment of the iron crystals in the portion of the inner core sampled by the waves that produced the anomaly is different from the alignment that the historical data had established as the baseline. The question of how the fabric of the solid inner core could change on the timescale of decades, the timescale of the monitoring record over which the change appears to have occurred, is one that the geodynamics community is actively wrestling with. The inner core is solid, but it is not rigid in the way that the mantle and crust above it are rigid on human timescales. Under the extreme pressures and temperatures of the deep Earth interior, iron is ductile, capable of slow plastic deformation over long timescales. The question is whether the deformation of the inner core can occur fast enough to produce a detectable change in the seismic fabric on the timescale of decades, and what physical mechanism could drive such a change. The interaction between the inner core and the outer core is the most likely source of any mechanism capable of driving changes in the inner core's behaviour on observable timescales. The outer core is a dynamic, convecting, rotating fluid that exerts both electromagnetic and mechanical forces on the solid inner core boundary. The electromagnetic forces arise because the electrical currents that generate the magnetic field flow through the electrically conductive iron of both the outer and inner core, and the interaction between those currents and the magnetic field they produce creates forces that couple the rotation of the inner core to the rotation of the outer core in a way that can transfer angular momentum between them. The mechanical forces arise at the boundary between the solid inner core and the liquid outer core, where the convective flow of the outer core impinges on the inner core surface and exerts a viscous drag that can influence the inner core's rotation and deformation. The geodynamo, the process by which the convecting liquid iron of the outer core generates the Earth's magnetic field, is one of the most complex physical systems studied in all of natural science. The magnetic field is generated by the same electromagnetic induction principles that govern the operation of electrical generators, but operating in a rotating, self-gravitating, compressible, electrically conductive fluid that spans a volume of nearly 270 billion cubic kilometers and that is subject to the Coriolis forces of the Earth's rotation, the buoyancy forces of thermal and compositional convection, and the electromagnetic forces of the field it is generating. The system is self-sustaining, meaning that the flow of the conducting fluid generates the magnetic field, and the magnetic field, in turn, influences the flow of the fluid in a coupled feedback that has maintained the geodynamo in operation for at least 3.5 billion years. It is also chaotic, in the mathematical sense that small differences in initial conditions produce large differences in long-term behaviour, which is why the magnetic field reverses its polarity at irregular intervals that range from tens of thousands to tens of millions of years, and why the intensity of the field fluctuates on timescales ranging from human lifetimes to geological epochs. The connection between the behaviour of the inner core and the behaviour of the geodynamo is a subject of active research that the anomalous signal from the inner core makes newly urgent. The inner core is coupled to the outer core through the electromagnetic and mechanical interactions described above, and changes in the rotation or deformation state of the inner core can in principle influence the pattern of flow in the outer core and thereby influence the behaviour of the geodynamo. The specific way in which this coupling operates and the timescales over which changes in the inner core propagate into changes in the magnetic field are questions that current geodynamo models address with varying levels of sophistication, and that observational data constrains imperfectly, because the magnetic field observations available at the surface of the Earth do not allow unique inference of the flow patterns deep in the outer core. The magnetic field has been declining in intensity over the period of systematic measurement, which spans roughly the past 2 centuries. The rate of decline has been approximately 5% per century, a rate that, if extrapolated linearly, would suggest a field intensity of 0 within approximately 2,000 years. The linear extrapolation is almost certainly not valid because the field has fluctuated in intensity throughout its history without going to 0, except during the brief transitional periods of polarity reversals. But the combination of a declining field intensity trend, an anomalous region of the field called the South Atlantic anomaly, where the field is significantly weaker than the global average, and where the anomaly has been growing in area and deepening in intensity, and now an unexpected signal from the inner core that may reflect a change in the deep interior process that generates the field, is a combination that the geomagnetic community is examining with the particular focused attention that scientists bring to a situation where multiple independent lines of evidence are pointing in the same direction. The South Atlantic anomaly is a feature of the Earth's magnetic field that has been recognized for decades and that has significant practical implications for satellite operations and for the radiation environment at high altitudes over the South Atlantic. The magnetic field is weakest in this region because the field geometry in the southern hemisphere below South America is inverted relative to the normal pattern, with a patch of reversed field polarity embedded in the main field that partially cancels the field in the overlying region. Satellites passing through the South Atlantic anomaly are exposed to higher fluxes of energetic particles from the Van Allen radiation belts than they are in other parts of their orbits, because the weaker field in the anomaly region allows those particles to penetrate to lower altitudes. The practical consequence is that satellites experience higher rates of electronic upset and component degradation when passing through the South Atlantic anomaly, and satellite operators have developed specific operational protocols for managing their spacecraft through the anomaly region. The South Atlantic anomaly has been growing. Its area has been expanding, and the minimum field intensity within it has been decreasing over the period of satellite observation. Paleomagnetic data, the record of the magnetic field direction and intensity preserved in the remnant magnetism of ancient rocks and sediments, indicates that the anomaly region has existed in some form for at least 1,000 years, and possibly much longer, and that its current behaviour is part of a longer-term trend rather than a sudden change. Some geomagnetic researchers have proposed that the South Atlantic anomaly is a surface expression of a large-scale feature of the core mantle boundary beneath the southern Atlantic, a region where the pattern of heat flow from the core into the mantle is anomalous, and where the resulting perturbation to the outer core flow produces the inverted field patch that manifests as the South Atlantic anomaly at the surface. If this interpretation is correct, then the growth of the anomaly may reflect changes in the dynamics of the outer core that are connected through the electromagnetic coupling of the core system to whatever is producing the anomalous signal from the inner core that the seismic network just detected. The core mantle boundary is the interface between the iron-rich liquid outer core and the silicate rock of the lowermost mantle, and it is one of the most dynamic and complex boundaries in the deep Earth. The temperature contrast across this boundary is estimated to be comparable to the temperature contrast across the Earth's surface, with temperatures in the outer core several thousand degrees higher than temperatures in the lowermost mantle just above. This enormous heat flux from the core into the mantle drives the thermal convection that is ultimately responsible for the plate tectonics operating in the crust above. The pattern of this heat flux is not uniform across the core mantle boundary. It is influenced by the structure of the lowermost mantle, which contains large-scale heterogeneities, including two enormous provinces of anomalously slow seismic wave velocity that are anchored beneath Africa and the Pacific, and that may represent thermochemical piles of dense material that have accumulated at the base of the mantle over billions of years of mantle convection. These large, low-shear velocity provinces, as they are technically called, influence the pattern of heat flow across the core mantle boundary, and thereby influence the pattern of convection in the outer core and the behaviour of the geodynamo. The relationship between the structure of the lowermost mantle and the behaviour of the geodynamo is a frontier of deep Earth research that has been advancing rapidly as computational resources have grown to the point where geodynamo models can be run at resolutions that begin to capture the influence of lateral variations in core mantle boundary heat flow. The models have shown that the pattern of heat flow at the core mantle boundary influences the location and strength of convective upwellings and downwellings in the outer core, the pattern of electrical current flow that generates the magnetic field, and the statistics of magnetic field reversals. These results connect the deep geologic history of the mantle, which records the history of plate tectonics and mantle convection over billions of years, to the history of the magnetic field recorded in the paleomagnetic record of ancient rocks. The connection between the surface record of plate tectonics and the deep record of magnetic field behaviour is one of the most ambitious integrations in all of Earth science, and the anomalous inner core signal that was just detected is a new data point that falls somewhere in that integration and whose significance cannot yet be fully assessed. The instruments that detected the signal are worth understanding in their own right, because the story of how humanity came to be able to listen to the Earth's deep interior is itself remarkable. The global seismic network that now provides continuous real-time monitoring of the Earth's seismic activity is the product of decades of international scientific cooperation and investment that began in earnest during the Cold War, when the detection of underground nuclear tests provided political motivation for developing a global network of sensitive seismometers. The Comprehensive Nuclear Test Ban Treaty Organization's international monitoring system, which includes a network of seismic stations distributed around the world specifically for the detection of nuclear explosions, is one of the most sensitive seismic networks on Earth and provides data that is used by the scientific community for research into the Earth's interior, in addition to its primary treaty verification function. The Federation of Digital Seismograph Networks, the Incorporated Research Institutions for Seismology, and national seismic networks operated by geological surveys in dozens of countries all contribute data to the global picture of the Earth's seismic behaviour that makes studies of the deep interior possible. The sensitivity of modern broadband seismometers is extraordinary. A high-quality broadband seismometer can detect ground motion of less than 1 nanometer, 1/1,000,000th of a meter, at periods ranging from seconds to thousands of seconds. At this sensitivity level, the instrument can detect the seismic waves from earthquakes occurring on the other side of the planet hours after the earthquake occurred, as those waves complete multiple traversals of the Earth's interior and continue to ring in the seismic record as the Earth's normal modes of free oscillation. The Earth's normal modes are the standing waves of the entire planet, analogous to the resonant frequencies of a bell that are excited by large earthquakes and that can be detected in the seismic record for days after the earthquake that excited them. The frequencies of the normal modes depend on the elastic properties and density structure of the Earth's interior throughout its full depth, and the measurement of these frequencies provides one of the most powerful constraints on models of the deep Earth available. The data from the global seismic network is archived and made publicly available to researchers around the world through data centers that maintain the full historical record of the network's operation. This publicly available archive is the resource that makes studies of the Earth's deep interior possible, because the signals from individual seismic waves that travel through the core are small, and their extraction from the seismic record requires the averaging of many events and many wave paths to pull the signal out of the noise. The archive of seismic data spanning multiple decades provides the statistical basis for detecting the kind of gradual change in inner core seismic behaviour that the current anomaly represents. The anomaly is not a sudden event that appeared in the seismic record at a specific moment. It is a trend, a gradual departure from the baseline established by the historical data that has been building over years and that has only recently become clear enough above the noise level to constitute a definitive signal rather than a possible artifact of data processing. The data processing required to extract core-sensitive seismic signals from the raw seismic record is itself a significant technical challenge that has driven the development of sophisticated analysis methods over the decades of deep Earth seismology research. The specific wave types most sensitive to the properties of the inner core are the ones that involve conversion between compressional and shear wave motion at the inner core boundary, that travel through the inner core as compressional waves and then convert back to shear waves in the outer core or mantle before arriving at the surface. These waves are designated with letter codes in the seismological nomenclature that indicate the wave types and boundaries they involve, and they arrive at the seismograph at specific times after the earthquake that generated them that depend very precisely on the properties of the material along their path. Measuring those arrival times with sufficient precision to detect the small changes associated with inner core rotation or fabric change requires careful accounting for all of the other factors that can affect wave travel times, including the three-dimensional structure of the mantle that the waves pass through on their way to and from the core, the properties of the seismic source itself, and the local site effects at the seismograph station that can shift the apparent arrival time. The researchers who first identified the current anomaly were doing so as part of a systematic study of the seismic wave travel time data accumulated by the global network over the past 3 decades, looking specifically for evidence of temporal change in the properties of the inner core that could constrain the rotation and deformation history of the inner core over the monitoring period. The study was motivated by the unresolved debate in the literature about inner core rotation rate and the conflicting results that different research groups had published using different datasets and analysis methods. The goal was to produce a more comprehensive and rigorous analysis than had been done before, using the full archive of available data and more sophisticated methods for correcting for the confounding effects of mantle heterogeneity and source variability. The anomaly in the polarization data was not what they were looking for. It emerged from the analysis as an unexpected feature that the rotation-focused analysis had not been designed to detect. The recognition of the polarization anomaly as a potentially significant signal rather than a processing artifact required the team to pause their primary analysis and examine the feature carefully, to test it against multiple alternative explanations, to look for it in independent datasets processed by different methods, and to conclude, after a period of careful scrutiny, that it was real. The realness of the signal, once established to the team's satisfaction through internal validation, required an explanation, and the explanations available within the framework of current understanding of the inner core were, in the preliminary assessment, insufficient. The signal was too large to be explained by the amount of inner core rotation that the existing models suggested had occurred over the relevant period. It was in a direction that was inconsistent with the fabric change that simple rotation of an anisotropic inner core would produce. It required either a more complicated rotation history than the simple models had assumed, or a change in the fabric of the inner core itself, or some combination of both. And the physical mechanisms available for changing the fabric of the inner core on the timescale of decades were, in the preliminary theoretical assessment, marginal. Not impossible, marginal. Requiring either flow velocities in the inner core that were at the upper end of what current models suggested was consistent with the observed seismic properties of the inner core, or forcing mechanisms at the inner core boundary that were stronger than current estimates of the electromagnetic and mechanical coupling between the inner and outer core. The electromagnetic coupling between the inner and outer core has been estimated from a combination of theoretical calculations and observational constraints, primarily from the magnetic field observations and from the analysis of the Earth's rotation rate, which is influenced by the exchange of angular momentum between the core and the mantle through the same electromagnetic coupling mechanism. The Earth's rotation rate varies on timescales ranging from daily to decadal, and the decadal variations are attributed primarily to the exchange of angular momentum between the liquid core and the solid mantle through electromagnetic torques at the core-mantle boundary. The amplitude of these decadal rotation rate variations constrains the strength of the electromagnetic coupling at the core-mantle boundary, and, by inference, the strength of the coupling within the core system. These constraints suggest that the electromagnetic coupling between the inner and outer core is strong enough to couple their rotation on timescales of years to decades, which is the timescale on which the inner core rotation changes detected by seismology are occurring. The question is whether the coupling is strong enough to drive the specific fabric change implied by the polarization anomaly. The answer to that question requires a theoretical framework for inner core deformation that is more sophisticated than what has been available in the literature, and the anomalous signal is providing the observational motivation for developing that framework. The inner core deformation problem involves the mechanics of a solid iron body at the conditions of the Earth's centre, approximately 330 gigapascals of pressure and approximately 5,000 to 6,000 degrees Kelvin of temperature. Under these conditions, the mechanical behaviour of iron is determined by the properties of its high-pressure phase, called hexagonally close-packed iron, or epsilon iron, whose elastic and plastic properties have been measured in diamond anvil cell experiments at high pressure, but whose behaviour at the extreme conditions of the actual inner core is extrapolated from those measurements using theoretical equations of state that carry significant uncertainties at the pressures and temperatures involved. The single crystal elastic properties of epsilon iron under inner core conditions, which determine the seismic anisotropy of a perfectly aligned iron crystal aggregate, are known from a combination of experimental measurements and first principles quantum mechanical calculations. The translation from single crystal properties to the observed bulk seismic anisotropy of the inner core requires a model for the texture of the polycrystalline iron aggregate that constitutes the inner core. Specifically, the distribution of crystal orientations and the degree of alignment. The texture is believed to develop through a combination of the crystallographic preferred orientation produced during solidification at the inner core boundary, the deformation that the inner core undergoes due to the forces applied by the outer core, and the annealing that occurs at the high temperatures of the inner core, which allow thermally activated processes to modify the crystal texture over geological time. The relative importance of these texture-forming and texture-modifying processes is uncertain and has been the subject of significant debate in the mineral physics and geodynamics literature. The anomalous polarization signal, if it reflects a change in the texture of the inner core, provides a new observational constraint on the rates at which these texture-forming and texture-modifying processes operate. A texture change detectable over the timescale of decades requires either a crystallographic preferred orientation development rate that is faster than most models have assumed, or a deformation rate that is larger than current estimates, or both. The signal is, in this sense, a stress test of the models of inner core dynamics, the same way that the heat dome was a stress test of the engineering systems of Phoenix. It is revealing the margins between what the models predict and what the Earth is actually doing. Those margins are narrower than the models suggested. The Earth is moving faster inside than the understanding of it had allowed for. The implications of a dynamically more active inner core for the broader Earth system depend on exactly what the dynamic activity is and what is driving it. If the inner core is deforming faster than models predicted, it is doing so in response to forces applied by the outer core, which means the outer core is exerting stronger forces on the inner core boundary than the current estimates of the electromagnetic and mechanical coupling suggest. A stronger coupling between the inner and outer core means that changes in the outer core flow, including changes associated with the magnetic field generation process, are more efficiently transmitted to the inner core and vice versa. The inner core is not a passive passenger in the geodynamo. It is an active participant, and the strength of its participation depends on how strongly it is coupled to the outer core that surrounds it. A more strongly coupled inner core that is responding more dynamically to the outer core flow would influence the pattern of outer core convection and thereby influence the behavior of the geodynamo. The specific influence would depend on the geometry and magnitude of the inner core deformation and rotation, which are precisely the quantities that the anomalous seismic signal is providing new constraints on. The connection between the inner core behavior implied by the signal and the magnetic field behavior recorded at the surface is not direct enough to allow immediate prediction of how the magnetic field will respond, but it motivates a closer examination of the relationship between the temporal changes in the inner core seismic properties and the temporal changes in the magnetic field that have been documented over the same monitoring period. The magnetic field observations over the past several decades have been made with increasing precision and spatial resolution as the observational infrastructure has improved. Ground-based magnetic observatories, geomagnetic satellites including the European Space Agency's Swarm constellation, and the historical record of magnetic measurements accumulated by ships and aircraft and ground surveys all contribute to the global picture of the magnetic field and its temporal variations. The temporal variations in the magnetic field include a broad spectrum of timescales, from the rapid variations driven by external sources in the ionosphere and magnetosphere, to the slower secular variation driven by changes in the core flow, to the very slow changes associated with the approach of a polarity reversal. The secular variation, the slow drift and change in the pattern of the magnetic field driven by outer core dynamics, has shown several features in the recent observational record that have attracted attention in the geomagnetic community. The rapid intensification of the South Atlantic anomaly has already been mentioned. An additional feature is the recent acceleration in the westward drift of the non-dipole component of the field, which reflects a change in the pattern of outer core flow that generates the non-dipole field. Another is the observation that the rate of change of the magnetic field, the secular variation, has itself been changing, with periods of relatively rapid change alternating with periods of slower change in a pattern that has been called geomagnetic jerks, and that has been the subject of significant research effort aimed at identifying its origin in the outer core dynamics. Geomagnetic jerks are abrupt changes in the rate of change of the magnetic field that occur over periods of months to a year, and that are global in character, affecting the magnetic field simultaneously across the entire planet. The abruptness of the change and its global coherence imply an origin in the core that involves rapid reorganization of the outer core flow pattern. The physical mechanism responsible for geomagnetic jerks has been debated in the literature for decades. The most widely accepted explanation involves torsional Alfvén waves, waves that propagate along magnetic field lines in the outer core and that can travel across the entire core in timescales of years, providing a mechanism for the rapid and coherent transmission of core flow changes from one part of the outer core to another. The connection between geomagnetic jerks and the inner core is one that has been explored theoretically, but not definitively established observationally. The inner core can reflect or absorb torsional waves reaching it from the outer core, and the way it does so depends on its physical properties and its coupling to the outer core. A change in the inner core's deformation state or rotation could modify its interaction with torsional waves in the outer core in a way that is reflected in the statistics of geomagnetic jerks at the surface. Whether the anomalous inner core signal is connected to any of the geomagnetic jerks observed in the recent record is a question that the research community is beginning to examine in the context of the new polarization data. The practical implications of geomagnetic jerks and of the broader secular variation of the magnetic field extend beyond academic interest in deep Earth dynamics. The magnetic field is used for navigation by everything from commercial aircraft to migratory birds to the bacteria that contain magnetite crystals and orient themselves along field lines. The World Magnetic Model, published jointly by the National Oceanic and Atmospheric Administration and the British Geological Survey, and updated on a regular schedule, provides the current best estimates of the magnetic field direction and intensity at any point on the Earth's surface, and is used in navigation systems, in the declination corrections applied to compass readings, and in the algorithms that convert magnetic sensor measurements to geographic directions in smartphones and other consumer devices. The World Magnetic Model has required emergency updates outside of its normal update schedule in recent years because the rate of change of the magnetic field, driven by the changes in outer core dynamics that are also reflected in the anomalous inner core signal, has been large enough that the model built at the last update was falling outside of its stated accuracy limits before the next scheduled update. The magnetic North Pole, the point on the Earth's surface where the magnetic field direction is vertically downward, has been migrating at an accelerating rate across the Arctic for the past several decades. For most of the 20th century, the magnetic North Pole was located in northern Canada. By the early 21st century, it had migrated across the Arctic Ocean and was approaching Siberia. The rate of migration has been increasing from approximately 15 kilometers per year in the early 20th century to more than 50 kilometers per year in recent years. This acceleration in magnetic pole migration reflects changes in the outer core dynamics that have been occurring over the same period, and that are connected, through the core system, to the inner core behavior that the anomalous seismic signal is characterizing. The birds that use the magnetic field for navigation have been the subject of significant research in the context of the magnetic field changes of the past several decades. The navigational abilities of migratory birds are among the most remarkable in the animal kingdom. Species that fly between breeding grounds in the Arctic and wintering grounds in South America or Africa, covering tens of thousands of kilometers in migrations that require navigation across featureless ocean and at night, use a combination of celestial cues, visual landmarks, and magnetic field sensing to determine their position and heading. The magnetic sensing, which is mediated by specialized cells in the bird's beaks and eyes that contain magnetite crystals and cryptochrome proteins, sensitive to the quantum mechanical effects of magnetic fields on chemical reactions, provides information about both the direction of the field and its intensity, which birds use to determine both their compass heading and their approximate latitude. As the magnetic field changes, both in direction and in intensity, the navigational information available to migratory birds changes with it. Whether the rate of magnetic field change occurring over recent decades is fast enough to meaningfully disrupt the navigation of migratory bird species is a question that ornithologists and biophysicists are studying with increasing interest and without fully definitive answers. The magnetic sensing systems of migratory birds appear to be calibrated to the local magnetic field during a period of development and learning, which should allow some degree of adjustment to slowly changing field conditions. But the rate of change of the field in the South Atlantic anomaly region and the rate of migration of the magnetic North Pole are among the fastest recorded in the paleomagnetic record for non-reversal periods, and it is not clear that the calibration and adjustment mechanisms of bird navigation systems were shaped by selection pressures that included rates of change this fast. The timing of disruptions to migratory bird navigation that have been documented in recent decades in the context of the concurrent changes in the magnetic field is a correlation that is being examined carefully, even if causation has not been established. The human sensory apparatus does not include a magnetic sense of the kind that birds and other animals possess, but the human technological infrastructure is profoundly dependent on the magnetic field in ways that are sometimes underappreciated. The magnetosphere, the region of space around the Earth that is dominated by the Earth's magnetic field, deflects the solar wind, the stream of charged particles emitted continuously by the Sun around the Earth. In the absence of a magnetosphere, the solar wind would interact directly with the upper atmosphere, stripping away the lighter atmospheric constituents through a process that has been proposed as a major factor in the loss of Mars's early atmosphere and in the transformation of Mars from a potentially habitable world with liquid water on its surface to the cold, dry, thin atmosphere desert it is today. The current magnetic field, generated by the geodynamo operating in the outer core, is strong enough to maintain a magnetosphere that provides effective shielding of the surface from the direct solar wind. During a polarity reversal, when the magnetic field intensity passes through a minimum that may be a tenth or less of its normal intensity, the magnetosphere would be significantly reduced, and the shielding effectiveness would be compromised. The implications for life, for the atmosphere, and for the technological infrastructure that depends on the magnetosphere for protection from solar energetic particle events would depend on the duration and depth of the field minimum during the reversal. The paleomagnetic record of past polarity reversals suggests that the field intensity minimum during a reversal can persist for thousands of years, during which the reduced magnetosphere allows enhanced cosmic ray and solar energetic particle fluxes to reach the surface. The biological effects of this enhanced radiation exposure are debated in the paleobiology literature, with some studies proposing correlations between reversal events and extinctions or evolutionary transitions in the biological record, and others finding no convincing correlation. The technical challenges of establishing causal relationships between magnetic field events that are dated with uncertainties of thousands to tens of thousands of years and biological events in the fossil record with similar dating uncertainties make definitive conclusions difficult. What is clear from the paleomagnetic record is that the biosphere has survived all of the reversals recorded in the geological record, which number in the hundreds over the past several 100 million years, without any reversal being associated with a mass extinction event of the magnitude of the end Cretaceous or end Permian events. This does not mean that a reversal would be without consequences for the modern world, because the modern world depends on technological infrastructure that is sensitive to electromagnetic effects in ways that no previous biosphere has been. It means that the biological risk from enhanced radiation during a reversal is probably manageable for the biosphere as a whole, while the technological risk deserves more specific assessment. The anomalous signal from the Earth's inner core does not predict a magnetic reversal. It does not even suggest that a reversal is imminent on any humanly relevant timescale. The connection between inner core dynamics and the probability or timing of a polarity reversal is not well enough understood to draw that conclusion from the signal. What the signal suggests is that the deep interior of the Earth is doing something that current models did not predict, that the system is more dynamic than the best available understanding suggested, and that the monitoring of the Earth's deep interior needs to be interpreted in the context of a theoretical framework that may require revision to accommodate what the data is now showing. The revision of a theoretical framework in response to anomalous observational data is the normal process of science. It is how understanding advances. The anomalous signal from the inner core is, in this sense, not a crisis for deep Earth science. It is an opportunity. An opportunity to identify the limitations of current models of inner core dynamics and to develop better models that can explain the anomalous observations. An opportunity to examine more carefully the connections between inner core behavior, outer core dynamics, and magnetic field evolution that current models have not fully captured. An opportunity to design new observational strategies, new seismic experiments, new modelling approaches that will extract more information from the data the monitoring network is collecting about the state and behaviour of the deep interior. The seismic network that detected the anomaly is being asked to provide more of this information than its current configuration can deliver. The spatial resolution of seismic imaging of the inner core is limited by the distribution of earthquake sources and seismic stations around the globe, which is highly uneven. The oceans, which cover 70% of the Earth's surface, have almost no seismic stations, creating a fundamental coverage gap that limits the ability to image the inner core from different angles, and therefore limits the spatial resolution of the inner core fabric map that can be constructed from the travel time and polarization data. Ocean bottom seismometers, instruments anchored to the seafloor and capable of operating for months to years before their data is recovered, have been deployed in research campaigns aimed at improving the coverage of the global seismic network in ocean basins. But their deployment is expensive, logistically challenging, and not yet at a scale that significantly changes the coverage problem for inner core imaging. Advances in distributed acoustic sensing technology, which uses fibre optic cables to detect seismic waves along their entire length by measuring the strain they produce in the cable, offer a potential path towards significantly expanded seismic monitoring coverage at lower cost than traditional seismometer networks. The submarine telecommunications cables that connect continents across the ocean floors represent an existing fibre optic infrastructure that, if instrumented for seismic sensing, could provide seismic monitoring coverage across ocean basins that is currently unavailable. Research projects aimed at demonstrating the feasibility of using submarine telecommunications cables as seismic sensors have shown promising results and are building the scientific and technical case for broader deployment. The translation from research demonstration to operational deployment requires the collaboration of the telecommunications industry, which owns the cable infrastructure, with the scientific community that would benefit from access to the seismic data, and with the regulatory and policy frameworks that govern the use of telecommunications infrastructure for non-telecommunications purposes. The computational resources available for modelling the Earth's deep interior have increased dramatically over the past decade and are continuing to increase at a pace driven by the broader trends in high-performance computing. The geodynamo simulations that model the convective flow of the outer core and the generation of the magnetic field have been advancing toward more realistic parameter regimes as computational power has grown, though they remain significantly far from the actual parameter values of the Earth's core, which are characterized by extremely low viscosity and extremely high electrical conductivity relative to what current simulations can achieve. The gap between the parameter regime of current simulations and the actual parameter regime of the Earth's core means that the simulations must be interpreted with caution, and that features of the simulated geodynamo may not faithfully represent features of the actual geodynamo. Closing this gap is one of the primary goals driving the development of the next generation of high-performance computing infrastructure for Earth science applications. The mineral physics experiments that characterize the properties of iron and iron alloys under core conditions have also been advancing, driven by improvements in diamond anvil cell technology, in X-ray diffraction techniques at synchrotron light sources, and in shockwave experimental methods. The determination of the melting point of iron at inner core boundary pressure, which sets the temperature at the inner core boundary and constrains the heat flux from the core into the mantle, has been the subject of intense experimental effort, because the melting point at these pressures could not be directly measured until relatively recently, and different experimental techniques had given discrepant results. The current best estimates of the melting point of iron at inner core boundary conditions have converged to within a relatively narrow range, but still carry uncertainties that translate into significant uncertainties in the heat flux from the core and in the age of the inner core, the time since the inner core began to solidify from the initially fully molten core. The age of the inner core constrains the thermal history of the Earth and the history of the geodynamo, because the geodynamo may have operated differently before the inner core existed to provide the compositional buoyancy that drives part of the convective flow in the outer core. The history of the geodynamo before the inner core formed is recorded in the paleomagnetic properties of ancient rocks, and paleomagnetic studies of very old rocks, those formed in the Archean and Hadean eons more than 2.5 billion years ago, have produced results that are not fully consistent with theoretical expectations for the operation of a purely thermally driven geodynamo. The intensities and directions of the ancient magnetic field recorded in Archean rocks suggest that the field was present and operating, but with characteristics that differ from the modern field in ways that may reflect the different thermodynamic driving of the pre-inner core geodynamo. The interpretation of these ancient paleomagnetic records is complicated by the alteration that rocks undergo over billions of years of geological history, and by the difficulty of establishing that the magnetic signal they carry was acquired at the time of rock formation, rather than during subsequent metamorphism or alteration. But the records are being used by the paleomagnetic community to constrain the timing of inner core nucleation and the history of the geodynamo across geological time, and the picture that is emerging from these studies is providing the long-term context within which the current behaviour of the inner core, including the anomalous signal just detected, needs to be understood. The inner core began to solidify from the initially fully molten iron core approximately 1 to 2 billion years ago, based on the best current estimates from both the paleomagnetic record and from thermal evolution models of the core. The uncertainty in this estimate is large because it depends on parameters, particularly the thermal conductivity of iron under core conditions, that have been the subject of experimental controversy. Measurements of the thermal conductivity of iron at high pressure, made by different experimental groups using different techniques, have given results that differ by a factor of 2 to 3, a discrepancy that translates directly into a factor of 2 to 3 uncertainty in the inferred age of the inner core. Resolving this discrepancy is one of the most important outstanding problems in core mineral physics, and multiple experimental programs are actively working on it using the most advanced high-pressure experimental facilities available. The age of the inner core matters for understanding the current anomalous signal, because the fabric of the inner core that the seismic anisotropy reflects is the product of all of the deformation and recrystallization that the inner core has undergone since it began to solidify. If the inner core is 1 billion years old, its fabric has been developing for 1 billion years and represents a long-term average of the deformation history over that period. If it is 2 billion years old, the averaging period is twice as long, and the fabric may be correspondingly more robust against rapid change. A younger inner core that has been accumulating its seismic fabric over a shorter time would be more susceptible to changes in that fabric from the current dynamics of the outer core. The anomalous polarization signal, if it reflects a fabric change in the inner core, is therefore potentially informative about the inner core age, in addition to the current dynamical state, because the rate of fabric change required to explain the signal is more or less plausible, depending on how long the current fabric has been developing. These connections, from the anomalous seismic signal to the inner core fabric, to the inner core age, to the thermal history of the core, to the history of the geodynamo, illustrate the integrative nature of deep Earth science. No measurement in isolation tells the full story. Every observation is a constraint on a system that is too complex and too inaccessible to be fully characterized by any single type of data. The anomalous signal from the inner core is one new constraint in a system of many constraints, and its interpretation will require integrating it with all of the other available information about the deep Earth, from the seismic tomographic images of the mantle to the laboratory measurements of iron properties under pressure, to the paleomagnetic record of the ancient magnetic field, to the satellite observations of the current field's secular variation. The scientists who went quiet when the data arrived are no longer quiet. They are writing papers, presenting results at conferences, debating interpretations in the peer-reviewed literature, designing new analyses of the existing data and new observational strategies to collect data that will better constrain the interpretation. The quiet was the moment of recognition that something unexpected had been found. The noise that follows the quiet is the process of science incorporating the unexpected finding into the ongoing project of understanding how the planet works. That process is slow, iterative, often frustrating, and ultimately the only reliable method humanity has developed for building accurate models of systems too complex and too large and too old to be studied by any other means. The Earth's core is not sending a message in the sense that it is trying to communicate something to the surface. It is doing what it has always done, convecting and conducting and solidifying and generating the magnetic field that makes the surface habitable, operating under the laws of physics that govern the behavior of iron at extreme pressure and temperature, indifferent to the network of seismometers listening to it from above. What has changed is not what the core is doing, but what the instruments are detecting, and what the analysis of those detections is revealing. The signal is new to the scientists. It is not new to the Earth. Whatever the inner core is doing, it has been doing it for some time, and the seismic record has been capturing it, waiting for a research team with the right dataset and the right analysis methods to look at the data in the right way and recognize that something in it required explanation that the current models could not provide. That recognition has now occurred. The explanation is being developed, the models are being revised, and the Earth's core, 5,000 kilometers below the surface, unconcerned with any of this, continues to do what it has been doing for billions of years, slowly solidifying, slowly spinning, slowly generating the field that holds the solar wind at bay and keeps the atmosphere in place, and makes all of the activity on the surface above it possible. The signal it has sent is not a warning. It is not an emergency. It is information. And information, in the hands of the people who know how to read it, is how the understanding of a planet that cannot be directly observed advances towards something closer to the truth of what is actually happening inside it. The truth of what is actually happening inside the Earth is a moving target. Every decade of seismological observation refines it. Every generation of mineral physics experiments constrains it more tightly. Every new geodynamo simulation run on a more powerful computer pushes the modelled parameter regime closer to the actual conditions of the outer core. The truth is not a fixed destination that the science is approaching along a straight path. It is a landscape that reveals itself gradually as the instruments improve and the analysis methods mature and the theoretical frameworks develop the sophistication required to make sense of data that earlier frameworks could not accommodate. The landscape of the deep Earth that has been revealed by the past century of seismological observation is one of the great achievements of 20th century science. Before seismology, the interior of the Earth was completely inaccessible to human knowledge in any quantitative sense. Philosophers and scientists had speculated about what lay beneath the surface since antiquity, producing theories that ranged from the geological plausible to the cosmologically baroque. The hollow Earth hypothesis, which proposed that the interior of the planet was a large empty space, potentially inhabited by unknown life forms, had adherents among educated people well into the 19th century. Edmund Halley, the astronomer for whom the comet is named, proposed a version of the hollow Earth hypothesis in 1692 that attempted to explain the secular variation of the magnetic compass by postulating multiple nested spherical shells rotating independently inside each other, each carrying its own magnetic field. The hypothesis was wrong in every detail, but the problem it was attempting to solve, the explanation of the observed changes in the magnetic field over time, was a real and important scientific problem that is still being worked on today, now informed by the knowledge of the actual structure of the Earth's interior that Halley did not have. The discovery that the Earth has a liquid outer core was made by the Irish seismologist Richard Dixon Oldham in 1906, based on his analysis of seismic wave travel time data from large earthquakes. Oldham noticed that certain types of seismic waves did not arrive at seismograph stations on the far side of the Earth from the earthquake, in the region that would later be called the shadow zone, and correctly inferred that a region of the Earth's interior was blocking the transmission of those wave types. The shadow zone is produced by the refraction of compressional seismic waves at the boundary between the solid mantle and the liquid outer core, the core mantle boundary, which acts like an optical lens that deflects the waves away from a region of the far side. The existence of the shadow zone provided the first seismological evidence that the Earth has a core with different properties from the mantle surrounding it. The inference that the core was liquid, capable of transmitting compressional waves but not shear waves, which require a solid medium for propagation, followed from the analysis of which wave types were and were not present in the shadow zone. The discovery of the solid inner core came 3 decades later, in 1936, when the Danish seismologist Inge Lehmann analysed the arrival of seismic waves in the shadow zone that should not have been present if the core were entirely liquid, and correctly inferred the existence of a solid inner core that reflected and refracted some of the waves back into the shadow zone region. Lehmann's discovery was made from the analysis of seismograph records of a single large earthquake and the careful comparison of the observed arrival times of waves in the shadow zone with the predictions of models with and without a solid inner core. The conclusion that the Earth has a solid inner core surrounded by a liquid outer core was a fundamental advance in the understanding of the planet's internal structure, and it was made by a lone scientist working with limited data and manual calculations at a time when the computational tools that modern seismologists take for granted did not exist. The recognition of Inge Lehmann's achievement was slow in coming. She continued to work in seismology until well into her 80s, making significant contributions to the understanding of the Earth's upper mantle, in addition to her foundational work on the inner core. She received the William Bowie Medal from the American Geophysical Union in 1971 and the Vetlesen Prize, sometimes called the Nobel Prize of Geoscience, in 1972. She died in 1993 at the age of 104, having lived long enough to see the global seismic network that she could not have imagined in 1936 transform the understanding of the interior structure that her work had helped to establish. The inner core that she discovered from the analysis of a handful of seismograph records is now being studied with a global network of hundreds of seismometers, generating terabytes of data per year, processed by computers of a power that would have been incomprehensible in her time. And it is still producing surprises that the best current understanding did not anticipate. The anomalous signal that has generated the current scientific attention is a surprise of exactly the kind that Lehmann's career exemplified. A careful analysis of existing data, motivated by a specific scientific question, producing an unexpected finding that requires a revision of the established understanding. The science of the deep Earth advances through exactly these moments, through the willingness of researchers to look carefully at data that others have looked at before, and to ask whether there is something in it that has not yet been recognized. The polarization anomaly that the current research team identified had been present in the seismic data for years before it was identified. The waves that carry the signal have been arriving at seismograph stations and being recorded in the archive throughout the period over which the fabric change appears to have been occurring. The signal was there. The analysis that revealed it required a specific combination of the right dataset, the right processing methods, and the right scientific question being asked. The right scientific question in this case was motivated by the unresolved debate about inner core rotation that had been generating conflicting results in the literature for more than 2 decades. That debate created the context in which a systematic re-examination of the core-sensitive seismic wave data was scientifically motivated, which created the opportunity for the polarization anomaly to be noticed. The sociology of science plays a role in which anomalies get noticed, and which ones wait for the right team asking the right question. An anomaly in a dataset that nobody is studying does not become a scientific discovery until someone looks at the dataset. The inner core rotation debate, whatever its eventual resolution, served the function of keeping the seismological community's attention on the core-sensitive wave dataset, and thereby creating the conditions under which the polarization anomaly could be found. The resolution of the inner core rotation debate itself may be illuminated by the polarization anomaly, because the two phenomena, the temporal changes in wave travel times that have been interpreted as evidence of rotation, and the temporal changes in wave polarization that constitute the new anomaly, may be different manifestations of the same underlying change in the inner core's state. If the inner core is both rotating and deforming, If its fabric is changing as well as its orientation, then the analysis of travel time changes alone may produce misleading results, because it assumes that the only change in the wave paths is the rotation of the anisotropic fabric, not a change in the fabric itself. The introduction of the polarization data as an independent observable provides a new constraint that can help disentangle the contributions of rotation and deformation to the observed changes, potentially allowing both the rotation history and the deformation history to be inferred simultaneously, rather than trying to extract one from data that conflates both. This kind of methodological advance, using multiple independent observables to constrain a system that cannot be directly observed, is characteristic of the progress that deep Earth science has made over the past several decades. The Earth's interior cannot be sampled directly below the first 12 kilometers of the crust, the maximum depth reached by the deepest borehole ever drilled, the Kola Superdeep borehole in Russia, which reached 12.2 kilometers after more than 2 decades of drilling before the project was abandoned in 1992. 12 kilometers. The center of the Earth is 5,000 kilometers below the surface. The deepest borehole in human history reached less than 0.25% of the way to the center. Everything known about the remaining 99.8% of the Earth's radius has been inferred from observations made at or near the surface. The Kola Superdeep borehole itself produced scientific surprises when it was drilled. The rocks encountered at depth were different from what geological models had predicted. The temperature at depth was higher than expected, reaching approximately 180 degrees Celsius at 12 kilometers, compared to the predicted 100 degrees. Free water was found at depths where it was not expected to be present, occurring as a gas-filled fracture network rather than as liquid water. The rocks showed evidence of biological activity, microbial organisms, at depths that were thought to be too hot and too isolated from the surface to support life. Each of these surprises was a reminder that the models of the Earth's interior, even at depths that are in principle accessible to drilling, are imperfect, and that direct sampling consistently reveals features that indirect inference did not anticipate. The surprises from the Kola Superdeep borehole were surprises about the upper crust, the outermost and most accessible layer of the Earth's interior. The surprises from the anomalous inner core signal are surprises about the deepest and most inaccessible part of the planet. The gap in accessibility between the two is enormous, but the gap in the conceptual challenge they represent is not as large as it might seem, because in both cases, the surprise is the same fundamental type. The Earth is doing something that the model did not predict. The model is wrong in some detail. The model needs to be revised. This is the repeating pattern of Earth science across every depth and every timescale, and it is the reason that the science remains productive and exciting, despite having been pursued for more than a century with increasing rigor and sophistication. The seismologists who are currently working on the interpretation of the polarization anomaly are doing so in a context shaped by the full history of inner core seismology that produced the anomaly to be explained. They are standing on the work of laymen and of the generation of seismologists who established the basic properties of the inner core in the decades after her discovery, and of the generation that discovered inner core anisotropy in the 1980s and proposed inner core rotation in the 1990s, and of the generation that has been debating the details of inner core rotation and deformation in the 2000s and 2010s. Each generation has added to the understanding. Each generation has also added to the list of things that are not yet understood. The current generation has a new thing to add to both lists. The polarization anomaly adds to the list of things observed. The explanation of the polarization anomaly adds to the list of things not yet understood. The work of adding the explanation to the list of things understood is now underway. The timeline on which that work will produce results is uncertain, as the timelines of fundamental research always are. Some aspects of the explanation may fall into place quickly, as the research community applies existing theoretical tools to the new observational constraint and finds that one of the existing models can accommodate the anomaly with minor modifications. Other aspects may require years of new modelling and new observations before the explanation is sufficiently constrained to be considered established. The history of inner core science suggests that the latter is more likely than the former, because the inner core has consistently resisted easy explanation, and because the phenomena associated with it, including the anisotropy, the rotation, and now the polarization anomaly, have all required extended periods of research and debate before converging on consensus interpretations. The extended period of research and debate that typically precedes consensus in deep Earth science is not a failure of the field. It is a reflection of the difficulty of the problem and of the rigor that the field applies to claims about a system that cannot be directly observed. The bar for claiming understanding of the Earth's deep interior is necessarily high because the opportunities for direct verification of such claims are extremely limited. A claim about the mechanical properties of the inner core cannot be verified by drilling a sample from the inner core and measuring those properties in a laboratory. It can only be verified by showing that the claim is consistent with all of the available indirect evidence, including the seismic observations, the magnetic field observations, the laboratory mineral physics measurements, and the results of geodynamo simulations, and that no alternative claim is equally consistent with all of that evidence. Achieving that level of consistency for a claim about the anomalous polarization signal and its cause is a research program that will take time. The public communication of deep Earth science during this period of active research and unresolved questions requires careful navigation of the tension between scientific uncertainty and public interest. The anomalous signal from the Earth's core is genuinely scientifically significant. It is not a crisis. It is not a harbinger of imminent catastrophe. The magnetic field is not about to collapse. The geodynamo is not about to stop. The inner core is not about to do something that will have consequences for the surface on any human timescale. What is happening is that the monitoring network has detected something that the models did not predict, and that detection has initiated the process of revising the models to accommodate the new observation. That process is the normal business of science. Its communication to the public requires honesty about what is known and what is not known, and resistance to the temptation to connect the scientifically interesting to the catastrophically alarming in ways that the evidence does not support. The history of science communication about the Earth's magnetic field includes numerous examples of claims that did not survive contact with more careful analysis. Claims about the imminent reversal of the magnetic field, about the consequences of a reversal for life on the surface, and about the connection between magnetic field changes and historical events in human civilization, have appeared in the popular science literature with a regularity that exceeds what the evidence actually supports. The paleomagnetic record does not show that past reversals were correlated with mass extinctions or civilizational collapses. The field has reversed hundreds of times in the geological record without catastrophic biological consequences. The current rate of magnetic field change, while elevated above the long-term average, and while producing the practical consequences for navigation and satellite operations described earlier, is not unprecedented in the paleomagnetic record and does not constitute evidence that a reversal is imminent on any timescale that should change how anyone plans their near-term future. What the anomalous inner core signal does constitute is evidence that the Earth's deep interior is a more dynamically active system than the current generation of models has captured, and that the monitoring of that system through the global seismic network and the satellite magnetic field observations is detecting real changes that deserve scientific attention and that will, through the normal process of research and model revision, advance the understanding of how the planet's deep interior works. That advance in understanding is valuable in itself, as the product of the human intellectual project of comprehending the planet on which civilization depends. It is also potentially valuable in practical terms if the improved understanding of deep Earth dynamics leads to improved models of the magnetic field's future behavior that can better inform the long-term planning of space weather resilience, of navigation infrastructure, and of satellite operations that depend on accurate knowledge of the magnetic environment. The practical value of improved deep Earth models is not primarily in predicting geological events on human timescales. Earthquakes, volcanic eruptions, and the other surface manifestations of the Earth's deep interior dynamics operate on timescales that are not controlled by the behavior of the inner core in any direct sense. The timescale on which the inner core's behavior matters for practical purposes is the timescale of the magnetic field, which operates on decades to centuries for the secular variation and on tens of thousands of years for polarity reversals. On these timescales, the improved models that the current research will eventually produce could contribute to better forecasts of the magnetic field's trajectory over the coming decades. which has direct practical relevance for the design and operation of systems that depend on the magnetic environment. The space weather consequences of a significantly weakened magnetic field, which could occur during the approach to a polarity reversal over a timescale of thousands of years, are a legitimate long-term planning consideration for civilizations that will depend on satellite infrastructure and electronic systems for communication, navigation, and the management of power grids. The current generation of power grid infrastructure was designed for the solar storm environment associated with the current magnetic field intensity. A significantly weaker magnetic field would allow more intense geomagnetically induced currents during solar storms, currents that flow through the long conductors of the power grid and can damage or destroy transformers and other critical components. The Carrington event of 1859, the largest recorded solar storm in the instrumental era, caused widespread disruption to the telegraph systems of the time and would, according to current assessments, cause trillions of dollars of damage to the modern power grid if it occurred today under the current magnetic field conditions. Under conditions of a significantly weakened field during the approach to a reversal, the damage from an equivalent solar storm would be larger. Planning for this scenario requires understanding the trajectory of the magnetic field over centuries to millennia, which requires understanding the deep Earth dynamics that drive the field's secular variation and long-term evolution. The anomalous inner core signal is a small piece of that understanding, a new data point in the effort to characterize the dynamic behavior of a system that operates at the center of the planet under conditions of extreme pressure and temperature, and that generates, through the physics of electromagnetic induction in a rotating conducting fluid, the field that makes the surface of this planet a habitable environment for the life that has evolved on it over 4 billion years. The signal is small in terms of the physical changes it reflects. A change in the seismic fabric of the inner core that is detectable in careful analysis of decades of seismic data, but that has no perceptible consequence for the surface today. It is large in terms of what it implies about the current state of understanding of the deep Earth, and about the work required to bring that understanding into alignment with what the data is showing. The work is being done, the models are being revised, the analysis methods are being refined. The monitoring network that made the detection possible is being maintained and slowly expanded. The archive of seismic data that holds the full record of what the network has been detecting is being preserved and made accessible to researchers who may find in it anomalies that the original processing did not recognize. The mineral physics laboratories that constrain the properties of iron under core conditions are continuing their experiments. The geodynamo modeling groups are running their simulations on successively more powerful computers and advancing toward parameter regimes that better represent the actual conditions of the outer core. All of this is happening simultaneously with the extraordinary complexity and noise of the surface world, largely invisible to the attention of people who are focused, reasonably and necessarily, on the immediate demands of their own lives. The Earth's core does not compete for attention with the other events and concerns that fill the awareness of people living on the surface. It simply continues to operate 5,000 kilometers below the feet of everyone who has ever lived, generating the field that makes their existence possible, cooling slowly over geological time, solidifying incrementally at the inner core boundary, spinning at a rate that differs slightly from the rate at which the surface spins above it, and occasionally sending signals through the rock and metal of the mantle above that, if someone is listening with the right instruments and asking the right questions, reveals something new about the system that has been operating continuously since before the first self-replicating molecule assembled itself in a shallow Archean sea. The scientists who went quiet when the data arrived are the people who are listening. They went quiet because what they heard was new. They are no longer quiet. They are telling each other, and eventually the rest of the world, what they heard, and working to understand what it means. That process, the process of listening and understanding and explaining, is what science is. And the Earth, which has been doing what it does for 4.5 billion years without any audience, continues to do it regardless of whether anyone is listening or not. The listening is for the benefit of the listeners. The Earth requires nothing from us. We require everything from it. The signal from the core is a reminder of how much of what we require from it we do not yet fully understand. The seismometers are running. The archive is growing. The analysis continues. The models are being revised in response to what the data is saying, slowly and carefully, and with the rigor that claims about a system this inaccessible demand. And somewhere in the data being collected today, in the seismic waves arriving at stations around the world from the thousands of earthquakes that will occur in the coming months and years, there are signals that have not yet been identified that will, when the right team looks at the data in the right way, reveal the next thing that the Earth's deep interior is doing that the current understanding did not predict. The surprise that comes from the Earth is not a failure of the science. It is evidence that the science is working, that the instruments are sensitive enough to detect what the planet is doing, and that the scientists are attentive enough to notice when what the planet is doing does not match what the models said it would do. The next surprise is already in the data. It is waiting for someone to find it. The Earth will not announce it. It never does. It simply operates, and the signals it sends through the rock travel upward through the mantle and arrive at the seismograph stations, and are recorded in the archive and wait, patient as geology, indifferent as physics. Already there, already real, already telling a story that nobody has yet learned how to read. The listening continues, the understanding grows, the planet keeps its own counsel, and the distance between what is known and what remains to be known about the system at the centre of the Earth that makes the surface of the Earth habitable is smaller than it was a century ago, and larger than the questions currently being asked will ever fully close. That gap, the permanent productive gap between observation and understanding in the science of a planet that cannot be directly examined, is where the work of deep Earth science lives, and where it will continue to live for as long as human beings are curious about the world beneath their feet. The inner core sent a signal. The scientists heard it. They are working on what it means. The Earth is not waiting for an answer. It has never waited. It simply is, and continues to be, in ways that the instruments at the surface are slowly, imperfectly, and irreplaceably learning to read. 2143. The inner core does not know it sent a signal. It does not know that the waves it shaped as they passed through it travelled upward through 5,000 kilometres of rock and metal, emerged at the surface, were captured by instruments built by human beings, and were preserved in an archive where they waited until a research team looked at them carefully enough to notice that something had changed. The inner core is not aware of the scientists who went quiet when the data arrived. It is not aware of the papers being written, the models being revised, the conferences where the anomaly is being debated, the graduate students running new simulations on supercomputers, trying to reproduce the fabric change in a numerical model of the Earth's deepest interior. The inner core simply is. A solid ball of iron, roughly the size of the Moon, sitting at the centre of the planet at temperatures comparable to the surface of the Sun, under pressures that compress the iron into a crystalline structure that does not exist anywhere on the surface of the Earth, rotating slightly differently from the planet above it, growing incrementally as iron solidifies onto its surface from the liquid outer core that surrounds it, slowly accumulating the fabric of crystal alignments that the seismic waves read as they pass through. It has been doing this for somewhere between 1 and 2 billion years. It will continue doing it for billions more, long after the monitoring network that detected its signal has been replaced by technologies not yet imagined, long after the civilization that built the seismometers has been replaced by whatever comes next, long after the questions being asked about it today have been answered and replaced by new questions that the answers to the old ones make possible. What the inner core is doing matters for the surface in ways that are not immediate and not dramatic, but are as fundamental as anything in the natural world. The geodynamo that the outer core sustains, and to which the inner core is coupled through the electromagnetic and mechanical interactions that the anomalous signal is helping to characterize, generates the magnetic field. The magnetic field maintains the magnetosphere. The magnetosphere deflects the solar wind. The solar wind, without the magnetosphere to deflect it, would slowly erode the atmosphere. Without the atmosphere, the surface of the Earth would be like the surface of Mars, cold, dry, airless, silent. The signal from the inner core is, in this sense, a signal from the process that makes the silence impossible, that makes the noise of the surface The noise of weather and biology and civilization, and the questions that civilization asks about the planet it inhabits, possible at all. The inner core is not sending a warning. It is not announcing a crisis. It is doing what it has always done, in a way that the instruments have only recently become sensitive enough to detect, and that the science has only recently become sophisticated enough to partially interpret. The seismometers are running. The archive is growing. The work continues. And 5,000 kilometers below the surface, in the place that no instrument has ever directly reached and no human being will ever visit, the iron keeps solidifying, the crystals keep aligning, the fabric keeps accumulating, and the waves that pass through it keep carrying the record of what it is doing toward the surface, where someone is listening. The Earth is speaking the only language it has. The question has always been whether anyone is paying close enough attention to hear it.